2.5 is a rather lengthy problem, so let's start right away, sort of with part A. We are given a particle in our infinite square well, which we've been dealing with all this time for section 2.2, and it has some initial wave function that is a mixture of the first two stationary states. So we say, okay, psi of x comma 0 is going to be equal to little psi sub 1 plus little psi sub 2. In part A, our goal is to normalize our time equals 0 wave function and find A. So let's do that first by sort of writing out the rule for normalization. So our requirement is that the integral, and here we're going to be defining our integral inside some square well. So let's say that the well is located from 0 to a, as we've always been doing so far. So from 0 to a of the magnitude of our wave function squared, so magnitude psi of x comma 0 squared dx must necessarily equal 1. Whoops, that is a horrible one. I'm sorry. Okay, let's do this. So first off, obviously, we take the a term and move it out of the integral. So the magnitude of a squared times the integral from 0 to a. And then from here, we're going to write this out in full. So remember that the magnitude squared of psi, since psi can be complex, is going to be the complex conjugate of psi multiplied by psi itself. So the complex conjugate of psi 1 plus psi 2 is just going to be psi 1 star plus psi 1 2. Psi 2 star, sorry. So let's just write that out. So this is going to be psi 1 star plus psi 2 star. And this is going to be multiplied by psi 1 plus psi 2. dx. And this necessarily equals 1 due to normalization. And hopefully from here you sort of instantly see that we can take advantage of the orthonormality that we've been describing earlier to sort of instantly solve this. Because if we distribute out everything in these two binomials, what we get is magnitude of a squared at the front as before times our integral from 0 to a. And here we have magnitude psi 1 squared, because we have psi 1 star times psi 1. And we're going to add psi 1 star times psi 2 plus psi 2 star times psi 1, which is just the middle terms getting multiplied. And then finally, plus the magnitude of psi 2 squared, because we have psi 2 star times psi 2 at the end. And this, all of this capped off with dx, must equal 1 by normalization. And from here, this should be trivially easy, because due to orthonormality, the integrals of these two instantly just go to 0 because they are different n values. So because of that, we now have magnitude of a squared, and then these two cancel out. These two sort of just become 1 because, once again, orthonormality. So the middle terms equal 0 due to orthogonality, and then the n terms, the first and last term, equal 1 due to normality. So combined, this sort of concept is called orthonormality, where the integral over all of space of a psi function multiplied by another psi function is either equal to 1 or 0. 1 if the n values are equal, so 1 and 1 for the first term and 2 and 2 for the second term, or they equal 0 when the n values don't equal, such as 1 and 2 or 2 and 1. So because of that, we now have a squared times 1 plus 0 plus 0 plus 1, which is just now 2, and this has to equal 1. So we just move everything over to one side, and now we have a is equal to 1 over the square root of 2. Part B has two portions. First, we want to find the general wave function that is dependent on time, big psi of x comma t, and then we want to find its magnitude squared. And then we also want to express the latter expression as a sinusoidal function of time with the simplification of expressing omega as pi squared h bar over 2ma squared. So let's start with this first part, which is to find big psi of x comma t. And luckily, the textbook has basically walked us through step by step how to solve these types of problems. We know that the stationary solutions for our infinite square well, or any stationary system in general, forms a complete set, meaning that any function can be expressed as a linear combination of them. So since we can express any linear or any function in general, there's nothing stopping us from writing our psi of x of t, which is what we want for our specific system, as just a linear combination, summation of n of all of our stationary states for our infinite well. So Cn little psi n phi n. And then from here we take advantage of the fact that phi n is a purely exponential term and recognize that if we set psi at t equals 0, then we get the exact same coefficients. So it's still Cn, and then psi n remains the same because it has no time dependency. And then phi of n is an exponential in terms of t. So at t equals 0, it just becomes e to the power of 0, which is just 1. So phi n effectively drops out when we define psi of x comma 0 after defining our psi of x comma t in this way. From here, it's just a matter of finding the Cn's. And we know from Fourier's trick that the solution for finding the Cn is just writing Cn being equal to the integral of psi n, respectively, its complex conjugate, multiplied by our arbitrary function, psi of x comma 0. So we already have psi of x comma 0, and we also found a, so let's just write this out now. This is going to be equal to, and we have a at the front, so we bring that out of our integral, multiplied by the integral from 0 to a, because once again we're dealing with a square well still, psi n star, and then multiplied by our sort of combination of psi 1 and psi 2 states, psi 1 plus psi 2. And from here, hopefully you see obviously that the way to solve this is the exact same as before. We exploit orthonormality. So from here, we recognize that, well, let's write C in here. So we recognize that if we're trying to find n equals 1, then this is just going to be equal to, and we're going to replace the psi n star with 1, in which case we have psi 1 star times psi 1 plus psi 1 star plus psi 2. Due to orthonormality, psi 1 star times psi 2 integrates to 0, whereas psi 1 star times psi 1 just becomes 1. So C1 is just going to be equal to A. And if we do C2, this is the exact same thing. We're just flipping the order. Now we have A times the integral psi 2 star times psi 1 plus psi 2 star times psi 2. So the first term integrates to 0 due to orthonormality. So because of that, C2 is also equal to A. So therefore, C1 equals C2 equals 1 over the square root of 2. And we can keep on going all the way up to infinity, but this should very obviously show that, you know, anything other than 1 or 2 is just going to integrate to 0, because if it's 3, for example, then we have psi 3 star times psi 1 plus psi 3 star times psi 2, both of which do not equal each other in the n number count. So because of that, both terms integrate to 0, and the same is true for 4, 5, 6, 7, etc., so on, so on. So C1 and C2 are both equal to 1 over root 2. From here, we can just write out the full expression. Our big psi of x comma t, well, we know now that any c terms greater than 2 are equal to 0, so this is just the sum of two terms, C1 little psi 1 little phi 1 plus C2 little psi 2 times little phi 2. And from here, it's just a matter of filling this in. So first off, C1 is 1 over root 2. Psi 1 for our infinite square well is going to be equal to square root of 2 over a times sine of n pi x over a, or since n is 1 here, pi times x over a. Phi 1 is just our exponential wiggle factor that we described way earlier. It is just equal to the exponential e to the power of negative I times e1 times t all over h bar. And here we're going to sort of add on the second expression, added with, and then 1 over root 2 again, times square root of 2 over a, this time sine of, and since we're doing little psi 2, sine of 2 pi times x over a, and then once again our exponential wiggle factor, e to the power negative I, this time e sub 2 times t all over h bar. Apologies for the squished writing over here, running out of space. But from here, we can simplify this expression a little bit. First off, if you still remember, the energy values that our infinite square wall can take are equal to n squared times pi squared times h bar squared all over 2ma squared. And if we do what Griffiths told us to do at this beginning and to simplify using the constant omega, this is actually just equal to n squared times omega times h bar. Because we earlier said that omega should equal pi squared h bar over 2ma squared. So we're doing that here. And if we do that, our psi expression is going to be simplified considerably. X comma t is going to be equal to, and we're going to simplify some more by sort of getting these constant out. So it's going to be 1 over square root of a, and then multiplied by the same sign expression as before, and then multiplied by e to the power of, and this is e1, so en is equal to n squared omega h bar, so negative I times e1, which is going to be omega h bar, and since we have an h bar underneath, it's just going to be negative I omega times t, and then we're going to add this with, once again, 1 over square root of a, because the square root of 2 cancels on the top and the bottom. Same thing, sine of 2 pi over 2 pi x over a, my apologies. And then e to the power of negative, and here we have e sub 2, so this is going to be 4 now, so negative 4 I omega t. And this is our fully simplified sort of solution. From here, our next goal is to take magnitude psi squared and find that as well. So we can do that. So obviously we know that the complex conjugate of psi of x comma t is just going to be equal to everything being the exact same, except we're reversing the signs on our exponentials. So let's get rid of the negative here and get rid of the negative here. And if we multiply these together, we are going to get, let's see. First off, let's organize this by taking the 1 over square root of a and distributing it out and squaring it. So we have magnitude psi squared is going to be equal to, and we have 1 over a distributed out at the front, and then a bunch of terms. So let's start first off these two. So this is just sine squared because the exponentials cancel. So sine squared of pi times x over a. Second is this term and this term. So this is going to be let's see, sine plus sine of pi x over a times sine 2 pi x over a, and this is already looking to be a very tediously long expression, unfortunately. And then we have e to the negative I omega t times e to the 4 I omega t. Well, the exponents just add, so this is e to the 3 I omega t. Next off, we have the second term multiplied onto the first term. So once again, sort of this sine of pi x over a times sine of 2 pi x over a that we're adding on. So we're going to add sine of pi x times sine of 2 pi x over a, and then we have our exponential, which is going to be e to the power of, and here we have e to the negative 4 I omega t, sorry, multiplied by e to the positive I omega t. So this is going to be e to the negative 3 I omega t. And finally, multiplying the last term here by the last term here, which is going to just give us sine squared 2 pi x over a, because negative 4i omega t multiplies with positive 4i omega t to get just 1. So we're going to add this finally with sine squared of 2 pi x over a. And close, and this is technically our answer. However, part B says that we should express our magnitude psi squared as a sinusoidal function. And here we evidently have some exponentials that we sort of can't seem to get rid of. So we're going to get rid of them by using Euler's sort of law, which is that any complex exponential e to the ix can be expressed as cosine of x plus I sine of x. So if we do that, then what we're going to get is we're going to get the same thing as before, but we're going to sort of distribute out some things first off. So we have 1 over a times all of this, and note that sort of we share these front terms, sine of pi x over a times sine of 2 pi x over a, and we're going to multiply that by e to the 3i omega t plus e to the negative 3i omega t. And then we're going to close it off again as before, plus sine squared of 2 pi x over a. And from here, we can use Euler's law and sort of simplify this out. So this is going to become sort of, let's see, so this is going to be cosine of 3 omega t plus I sine of 3 omega t, and then plus cosine of negative 3 omega t plus I times sine of negative 3 omega t. And instantly, hopefully you see that sort of there's cancellation here, because sine is an odd function. Sine of negative x equals actually negative sine of x. So we can change this around. We can erase the negative here and move it out to the front effectively. And that instantly sort of allows us to cancel these two terms. Cosine is an even function, so cosine of negative x is actually effectively identical to cosine of positive x. So this is actually going to equal 2 cosine of 3 omega t. And from here, we just have to plug that back in. So we have, let's get this going first. So we get 1 over a plus, and we're going to move this over to this side, and we're going to include our sort of 2 cosine of, let's move this a little bit more for now, 2 cosine of 3 omega t, and then multiply it by our sine of pi x over a times sine of 2 pi x over a, and then we add on at the end the sine squared of 2 pi x over a. And this is our final magnitude squared solution. It's a very messy expression, but we have managed to do what Griffiths asked, and we have managed to sort of simplify down our exponentials into this trigonometric function. Part C asks us to find the expectation value of x, and this is a very painful calculation. So let's do that first. So we already know the general method for finding expectation values. We have mag psi squared here, and since we're finding expectation value of x and the operator for x is just x itself without any sort of fancy derivatives that we have to apply, it is literally as simple as sort of turning it into this expression where we have the expectation value of x equal to, and we bring the 1 over a out of our integral, times the integral from 0 to a of our answer from part B, and then we just attach an x at the front and we close off this integral with a dx at the end. This is obviously a very painful integral. We have to split it into 4 or 3 different ones: x sine squared, x times cosine times sine times sine, and then x times sine squared again at the end. Each one of these can be further split into more sub-integrals, because you have to use integration by parts to evaluate x times sine squared pi x over a. You have to take advantage of both u sub and integration by parts, and also sort of multiplication to some trig identities for this middle term, and you have to do integration by parts yet again for this final term. So I'm just sort of going to go over the concepts that we're going to do here, and then after that I will just sort of plug this into my magical integral calculator and give the final answer. Because if we actually did this out fully, it would literally probably take us like 45 minutes, and simply I just don't believe that it's worth it to spend that much time covering a math integral when this is supposed to be a physics course. So let's start right away with the first and last expression. So we have term number 1, which we'll express as an integral of x sine squared times pi x over a. And actually this is not just one. We're going to say that, whoops, I'm gonna call this term 1/3, because this applies to both of these terms. So we have an integral of this, and then we have an integral of x sine squared times 2 pi x over a times dx. And the way to solve these two component integrals is the exact same thing. We're going to take advantage of the power reduction trig identity, which states that basically sine squared of any variable, let's just call it x, is going to be equal to 1/2 times 1 minus cosine of 2x. So if we shove this in to like sort of both of these component integrals, then we're going to be able to like distribute them out from 2 integrals into 4, and 2 of those 4 integrals is just x times 1, so x, which becomes trivial, and the remaining 2 are both x times cosine of 2x, or x times cosine of whatever the 2x becomes after we sort of plug this in, but x times cosine of something, and both of those can be evaluated using integration by parts. So because of that, that's how you evaluate the first and third terms. That is already a very long and tedious process, but term number 2 is even worse, because term number 2, what we're going to do is we're going to solve this by using something called the product to sum trig identity. So let's start by writing this out. So term number 2 is an integral of x times cosine of 3 omega t times sine pi x over a times sine 2 pi x over a dx, where I'm excluding all of the constant numbers because those don't actually play a role in our integral anyway. First off, we can instantly sort of get rid of the cosine 3 omega t because that has no x dependency, so we don't actually bother with it. It just moves out of our integral as a constant. Whoops, I did not want to do that. Take this and move it closer. So we have x times sine of one thing times sine of another thing. And to simplify this down, we're going to use product to sum trig identity, which basically states that whenever we have sine of one variable x times sine of another variable y, we can convert this into the expression of 1/2 times cosine of x minus y minus cosine of x plus y. And if we do this, then instantly x sort of distributes to each of these terms, and then we can solve this by using 2 integration by parts on each of the component integrals. So the final count is that this integral sort of dissolves into, let's see, we get 4 from this, 6, we get 6, and then 7, 8, 9. This actually dissolves into 10 component integrals. So this is a very horrible, very mean and messy equation. Thankfully, we are studying physics, so I'm just going to shove this into my magical integral calculator and tell you that the final result for this is going to be equal to a over 2 minus 16 times a over 9 pi squared multiplied by cosine of 3 omega t. Okay, so we have our answer that we got from our magical integral calculator. Now it's asking, what is the angular frequency of the oscillation and what is the amplitude of the oscillation? Well, the amplitude is very easy. It's just 16a over 9 pi squared. The frequency is 3 omega because we have cosine of 3 omega t. So we know f equals 3 omega. And then amplitude equals 16 times a over 9 pi squared. And from here, the other sort of note that Griffiths makes is that our amplitude should not be greater than a half. And if we sort of plug this into our calculator, this is actually, this is going to give us roughly 0.18 a, which is obviously less than 1/2 times a. So we are sort of, we can gladly say that our result does in fact check out with what Griffiths said we're supposed to get. 0.18 is obviously less than 0.5. So our answer apparently does make sense from that sanity check, from the perspective of sort of that sanity check. Part D asks us to compute the expectation value of momentum. Now, if you remember, the operator for momentum is negative I h bar partial with respect to x, and hopefully you see that that is even more painful of a calculation to do than the expectation value for x, because x already gave us sort of this subcomponent of like 10 different subintegrals. If we have to derive one of the terms first before doing this, it's only going to get worse. However, there is evidently a hint here in that there is apparently a much easier way to actually solve this. And there is, because if we sort of go back to our memory of chapter 1 when we started talking about expectation values, the way we actually derived the operator for p in the first place was that by saying that, well, the expectation value of p, well, momentum is just mass times velocity, so there's nothing stopping me from just saying that p can be, the expectation value of p can be written in terms of the expectation value for x, and just say that p equals mass times velocity, or dx over dt, or in this case d expectation value x over dt. And I really want to stress this because earlier on we actually did have a problem, I think back in chapter 1, where we were given a wave function and we were asked why using this method didn't give us the correct answer. And the reason for that is because in that specific problem back in chapter 1, the wave function we were given was psi of x comma 0, specifically defined at t equals 0. In this case, we have sort of already defined psi of x comma t right here. So we actually have the general time-dependent wave function, whereas in that earlier problem back in chapter 1, we were only defining psi of x comma 0, which is psi defined at one specific point in time. So because of that, in that problem, using this method actually did not give us a valid answer. It just gave us the trivial answer of expectation value of p equaling 0 when it didn't. But in this case, because of the fact that we have the full wave function in terms of both position and time, we have psi of x comma t for all x and all t, we are in fact allowed to use this shortcut. And doing this is obviously infinitely easier than sort of plugging and chugging our way through the general expression for doing this, which involves sort of deriving this mess that we sort of have up here. So instead, we're just going to do this. So this is going to be equal to m times the derivative with respect to time of our expectation value of x. So m times d over dt of our answer from part C, which is this expression right here. So we're going to shove it in, and this is infinitely easier to solve. The a over half just goes to 0, so this is equal to m times, let's see, negative 16 times a over 9 pi squared remains as such, and then we have sine of 3 omega t and we have to bring out a -1 because we're deriving cosine, and then finally we bring out the 3 omega. So overall, this finally becomes 16 times am times 3 omega times 9 pi squared at the bottom. The 3 cancels out with the 9, so let's just do 16 am omega. And let's replace the 9 with a 3 at the bottom. And then we have sine of 3 omega t. And this is our answer. We have solved it, and we've done it in a fraction of the time it would have taken had we gone the long route and actually derived out the integral that we normally would do. The final part of this problem is to find the expectation value of the energy. So let's do that right away. So first off, way back in this chapter, we sort of, one of the things we made a point about was that our coefficients, Cn, are actually equal to the probabilities of measuring. So Cn is actually equal to the probability to measure our general state in some specific, in, let's say, the nth stationary state. And what this means is that we're sort of going back to a point we made before, where that measuring a system sort of forces it to collapse in on itself into a specific value. So the wave function is only stable unless it's not being observed. And we sort of talked about this back in chapter 1 at the very beginning, where we talked about how observing things apparently sort of changes, it sort of intrinsically changes the universe in some manner. So the act of observation is somehow sort of fundamentally linked into the fabric of reality, and that observation is actually something that can physically change a system. So as a result of that, when we look at a system, its wave function will actually collapse. This is sort of the same idea, where if we have a general wave function that is expressed as a sort of summation of all of these individual wave functions, our coefficients actually end up being the probabilities of the wave function collapsing to any given wave function upon measurement. We have not proved this, and we won't prove it for quite a while. However, this is something that sort of, as I said earlier on, that Griffiths sort of gives us, and we have to take as just gospel until we get the tools to actually prove this. But if we do just sort of simply take this as true, we already know that magnitude C1 squared equals magnitude C2 squared, and they both equal 1/2. So evidently, for this given system, psi of x, comma 0 equals a psi 1x plus psi 2x. For this given system, at time equals to 0, if we measure it, there's an equal probability of the system collapsing into the stationary n equals 1 state or the stationary n equals 2 state. So if we sort of did this, well, obviously then sort of we already know what the energy values are. We know that E sub 1 for the stationary n equals 1 state is just equal to h bar omega. And we also know that E sub 2 for the n equals 2 stationary state has an energy of 4 h bar omega. So if we wanted to calculate the average energy, then that's just a matter of saying the expectation value of h, which is our Hamiltonian, which gives us our expected energy, is going to just be 1/2 h bar omega plus 2 h bar omega, because 4 h bar omega divided by 2 is just 2 h bar omega. And this is, 2.5 h bar omega, which lies between our E1 level and our E2 level. And the point that we sort of really want to make here is that the expectation energy is actually not physically possible to get, because remember, as we've said before, apparently in quantum mechanics, energy is actually a discrete value, unlike in classical where it is continuous. Unlike sort of a ball rolling down a hill where it can have an infinite sort of spectrum of energies, in quantum mechanics, sort of systems actually have well-defined energy values. So I can only have some energy E1 or some energy E2, and they jump up by a discrete value. It's not sort of this infinite continuous spectrum. So because of that, the expectation energy, or what the average energy that I get, is actually not sort of possible. We will never get that value. It's just simply the average of all of our discrete energy values in the system.